Abby, and this is Physics Lab number 1, Constant Velocity. So, the purpose of this lab was to apply Newton's laws of motion to a real-world example. This lab focused primarily on Newton's second law of motion, the momentum principle. This states that the acceleration of an object is proportional to mass and force, or force equals mass times acceleration, which can be rewritten in this format, which is the velocity update formula. If no net force is applied to an object, it won't have an acceleration, which means the object is either not moving or has a constant velocity. In this experiment, we look at an object with constant velocity and a theoretical model of an object with a constant velocity and compare them. So, results from this experiment. The ball rolling in real life did not have a constant velocity, and the experimental model did have a constant velocity, and we sort of went in depth with why. So here's the experiment. I rolled an orange ball across the floor. The system is an orange ball, and the surroundings are everything else, like the floor, earth, etc. Here's what everything looked like in Tracker. And this is me playing out the experiment in Tracker. Over here we have graphs that show the position versus time and velocity versus time. Here's the ball rolling across the screen with each of the data points being plotted per frame. Then you can see over here on the right, I have time and position data points. And these are the data points that I ended up putting into Excel to create a graph. So, initial conditions. I used this time this position right here, that was the initial position, and this was the initial velocity, initial time right here. Down here I have the initial velocity, which I put in right here. And right here, this is the ending time, so the experiment in GlowScript only continued until 1.894 seconds. This is what everything looked like in GlowScript. Here's the position versus time and velocity versus time, and you can see that velocity is constant, whereas position versus time increases linearly. Here's everything in GlowScript once again. This is just me running the program. And here's all the data, coding, etc. So here I run the program, and you can see that the orange ball moves at a constant velocity to the right, position increases linearly, velocity is constant the whole time. And the data points at the bottom is what I put into Excel. And here is when I inputted all the data into Excel so I could create a chart or a graph. So right here I have all of the times and all of the positions that correlated with each time from the actual experiment. And then right here is from the theoretical experiment on GlowScript. I have time on the left and position on the right. So then I input all of these data points into this graph right here, and I have predicted versus experimental position versus time. So the yellow is the predicted, which is what I ran in GlowScript, and the orange line is the experimental, which is what I did in real life with the orange ball. Here's the graph once again. Yellow line is theoretical, orange line is experimental, and you can see that this increases at a constant rate, and this increases, but you can see that the data points kind of curve upwards and then they dip below because velocity is slightly decreasing as the experiment continues. And you can also see that they start at the exact same position in time. There could have been a possible error with rolling the ball or the ball knocking into something not included in the experiment. So how would results change or stay the same if you were to flip the axes? So for example, the positive x and negative x change. This would result in a negative slope opposite of the graph produced when the ball traveled in the positive x direction. So in the experiment I ran with the orange ball, the ball was moving from left to right. However, in this graph right here, the ball would be rolling from right to left, and position would go in the negative x direction as time increased. So what does it mean? Is it possible to say how many pushes and pulls, forces, are added together to give zero net force in the case I observed? So we know that the net force is zero because of the constant velocity observed by the theoretical model, but it's impossible to tell the exact amount of pushes and pulls required to make the net force equal zero. In the real-life experiment, the initial force of my hand pushes the ball in the positive x direction, while the friction force from the ground is applied in the opposite direction. Even though it wasn't shown in the video, the ball rolling on the ground will eventually stop because the force of friction results in a net force in the negative x direction. So, in conclusion, when the experiment model was compared with the theoretical model, the initial velocities were identical. However, the initial velocity of the theoretical model perfectly matched the final velocity, whereas the experimental model displayed a decrease between initial and final velocity. In real life, a net force like friction will act upon an object and the object will not behave ideally. In a theoretical experiment with no net forces, the object will behave in accordance to Newton's laws of motion and have a constant velocity. The end.